So in this video, I want to connect some of the things that are definite integrals to elements of geometry, to specifically to computing the area under a graph. So this has been a bit of a theme in the class, although we haven't maybe gone into it as much as you would in some other classes. But in calculus, there's kind of an interplay between geometry and algebra. And we saw this at the very beginning of the class where we talked about tangent lines to curves or slopes to curves. And that was computed by the derivative and then we developed all these algebraic tools to compute the derivative. And so we solved problems about, involving the shape of graphs using calculus, using algebraic techniques from calculus. So when is a function increasing, decreasing, concave up, concave down? We kind of link those two ideas of geometry, shapes of graphs, and first derivative, second derivative, etc. Now, the same thing can be done in integral calculus, although there's a similar connection between the kind of computations and algebra of antiderivatives in integral calculus and areas under the graph. And so something about geometry of curves. Now, I won't be able to explain this very well in this case because it requires a lot more theory than what we went into in this class. But hopefully you'll get an idea of how to use it, and you'll see it in some examples, and you'll learn further that integration is a very powerful tool. So let me just and I'll try to explain in an example why this connection you might be inclined to believe this connection exists. All right, so in this setting, we'll let f of x be a continuous function on an interval and we will also suppose that f of x is non-negatively valued. So that means that, i.e., f of x is bigger than or equal to 0 for all x with x between a and b. Then here I'll state the connection between the algebra and the geometry, and then I'll investigate it in a simple case, and maybe you'll believe that it should be true, although, like I said, I won't be able to explain it to you in general. Okay, so then we can ask the following question. We can ask, how do we find the area under the graph of f between x equals a and x equals b? Okay, so let's draw a picture, just to give an idea of what kind of thing we're looking at. So say here's x equals a, here's x equals b, here's f of x, and you want to compute this area under the graph between a and b. So that's the question mark, right? What is that area? Okay, so here's the result. Here's the theorem, and I think the book calls this theorem 1. So in the homework, if there's oblique references to theorem 1, this is what they're talking about. So the definite integral from a to b f of x dx is the area under the graph of f between x equals a and x equals b. And like I said, this is a pretty amazing result, right? Because it connects like a calculus thing about antiderivatives, which is kind of I view as an algebra type thing, reversing the power rule, sum rule, all these kind of algebraic tools we have for computing definite integrals. And it connects to something very, very geometric, right? Namely the area under the graph. Okay, so why might this be true? Suppose that we have a function v is v of t is the velocity of a moving object. So we've talked about this before. And then we know that if we look at the definite integral from time t equals a to time t equals b of the velocity function, that we get the net displacement, or how far the object has traveled between time t equals a and time t equals b. Okay, now, so suppose for a moment that v of t is just some v0 is a constant function. Suppose it's a constant function. So i.e. the object's moving with constant velocity. Okay, so then we kind of know, without how to compute the the integral, or this definite integral, without even using calculus, right? I mean, but we can do it if we want. I mean, we can do the calculus if we want, but this is just the speed or the velocity times the length of the time interval, right? So for motion with constant speed, it's just the time you're moving times the speed you're moving. We talked about this at the beginning of the class. So if you're driving 100 miles an hour, in 2 hours you will have driven 200 miles. And 70 miles an hour, in 2 hours you'll have driven 140 miles, etc. So you can do the calculus here, but it's unnecessary. But look at this quantity here on the right-hand side of this equation. So it's just speed times the difference in time. If we were to draw the graph of this velocity function, right? So it's just constant velocity. So the graph is just a horizontal line at v naught, right? And this quantity here, v naught times b minus a, this is exactly the area of the rectangle with base, the interval between a and b, and height v naught. So that's exactly that area. So at least if you have motion with constant speed, you see that the definite integral represents the area under the graph of velocity versus time. Now, if the speed isn't constant, it's much, much harder to see the connection between these two things, that the displacement is the area under the velocity versus time graph. That is true according to this theorem, right? But that requires it would require going into much, much more advanced theory of the integral than we cover in this class, and really kind of understanding what this integral notation really is about and what it's actually deeply computing in some sense. But we won't go into that. So instead, here's an example for you to kind of believe why this might be true. And now we'll just play with this theorem that we can we can compute areas using definite integrals and so forth and so on. So now we'll just do a bunch of examples. Okay, so this first one's going to be really, really easy. So find the area under the graph of y equals x from x equals 0 to x equals 1 in two ways. A, using a classical formula from geometry. Calculus. And B, using calculus. Okay, so let's just draw a picture first. Okay, usually in these questions that often the picture is provided for you. Um, this is very, very simple. So hopefully you can construct the picture on your own, but in many cases they give you the picture anyway. So you'd have here the curve y equals x, right? This is a straight line. And what we're asked is to find the area under this curve between 0 and 1. That's just the area of this triangle, of this right angle triangle, right? This is a right angle here, right? So we want to find this area shaded in blue of this right angle triangle, right? And the dimensions of the triangle are clear. I mean, the base is length 1 and the perpendicular height is also 1. So if we use a classical formula, so the area of a triangle with base length 1 and height and perpendicular height height 1 is just right half the length of the base times the height, right? So it's half the length of the base. Oops, sorry. Times height, and that's just half. In this case, half times 1 is 1/2. Okay, so that's we just know from basic geometry. Now, if you want to do it with the calculus, you look at the integral. If you believe the theorem that theorem 1 that I mentioned, you look at the integral 0 to 1 x dx. Right, so this is, we have to compute an antiderivative of x evaluated at 1 and then subtract the result when we put in 0. So antiderivative of x, reversing the power rule, is x squared over 2. Then we evaluate at 1 and subtract the evaluation 0. We get 1 squared over 2 minus 0 over 2, or 0 squared over 2. That is just also 1/2. So here you see another instance of where the theorem is true. The calculus is giving you the answer you expect from classical geometry. So these answers are indeed the same. Okay, so I'm not going to spend the week computing things we know how to compute using geometry formulas, right? The point is to do things we don't know how to do, and that's we cannot do without calculus very easily. So that's what the next little stuff is going to be about. Okay, so and the picture, I'll draw the pictures provided in this case, but we will. I'll have to draw it for you, but on your homework, you'll get the picture. So don't worry about producing this picture, in other words. Okay, so here we go. So set up and evaluate the definite integral that gives the area of the shaded region. Okay, so then this is in this shaded region I have to give you. So here's what it is. So it's 1 to 4. The curve is this parabola minus x minus 1, x minus times x minus 4. And you kind of shade it in here. Okay, so we want to figure this out, the area under this parabola. Now, this is really difficult to do using classical geometry. There are some very old ancient geometric formulas that you can use. And if you're interested, I can tell you, but they're not something that you would learn in school anymore. Really, the way to approach this efficiently is to use calculus. Okay, so we need to compute the integral. The definite integral from 1 to 4 of minus x minus 1, x minus 4 dx. Now, to do this, we did an example like this with an indefinite integral last week, but you need to expand the function inside the integral to be able to use our sum rule and reverse power rule, etc., to be able to find the antiderivative you need. So first you have to expand the function inside the integral. So you get integral from 1 to 4. And I'll watch my parentheses here. So I'll do the minus last. So x squared minus 5x plus 4 dx. And now what I can do is I can actually move the minus. Well, maybe we should expand the minus. That's probably easier. Minus x squared plus 5x minus 4 dx. And now we can use our sum rule along with our constant multiple rule to evaluate the integral. So you integral from 1 to 4 minus integral of x squared plus 5, the integral from 1 to 4 of x dx. I drop the dx here, which I want to do. And then minus 4, the integral from 1 to 4 of just 1 dx. And now watch your parentheses, minus any derivative of x squared. That's up the power 1, x3 over 3 between 1 and 4 plus 5 times the antiderivative of x. We've done this many times. It's x squared over 2 between 1 and 4. And then antiderivative of 1 is just x, so it's minus 4 times x between 1 and 4. And so you can start putting in numbers. So minus 4 cubed over 3. 4 cubed is 64, so 64 over 3 minus 1/3. And then watch the parentheses here, right? This negative is multiplying this entire difference. Remember, this bar symbol is for a difference, right? Plus 5, 16 over 2, minus 1/2, minus 4, that's 4 minus 1. Okay, now this is a lot to compute by hand. I won't do it, but if you put it into your calculator, you should get 9/2, 9 over 2. Compute in a calculator. Okay, so this is something that you would have a lot of difficulty figuring out this area under a graph, just under this parabola, just from using basic geometry. There is a way to do it, but it's really, really not hard and not easy at all. Okay, so let us do something that actually that you have to do using calculus. Okay, so for the next example, it helps to remember the indefinite integral. So the integral of e to the kx dx is e to the kx over k plus c. So in other words, in particular, the function e to the kx over k is an antiderivative of the function y equals e to the kx. Okay, so that was something we talked about in the first antiderivative video. It's been a while. It's a good thing to have at your fingertips. And then in this section, it's also very important in general. Okay, so here's the third example. Below is the graph of the function y equals 3x squared plus 4x plus 5e x over 5. All right, so I'll give you the graph. You do not have to produce this. It looks something like this. And the question asks us to find the area of this shaded region. Find the area of the shaded region. Okay, so again, we have to compute the definite integral, right? So we're dealing, this is the graph of this function, 3x squared plus 4x plus 5 e to the x over 5. So I wanted to remind you of this formula for the antiderivative of e to the kx over k, because this will obviously be useful in this question. So here's the answer. According to the theorem, this area is given by the definite integral from 0 to 2, 3x squared plus 4x plus 5 e to the x over 5 dx. And again, we should use our rules about definite integrals to compute this guy. So this is 3 times the integral from 0 to 2, x squared dx, plus 4 integral 0 to 2, x dx, plus 5, the integral from 0 to 2, x over 5 dx. Okay, so now we know how to do all of these, right? So we need to find an antiderivative of x squared, evaluate 2, then subtract the result when we have evaluated 0, etc. So antiderivative of x squared is x cubed over 3, evaluate 2, subtract the result at 0. Antiderivative of x is x squared over 2, evaluate 2, subtract the result at 0. And then we get to this guy. I mean, it should go the line below here if you don't mind. Plus 5, antiderivative of e to the x over 5. So, right, this is e to the x over 5. So this is the formula. Where did it go? So now we're going to use this formula here with k equals 1/5. So you get here, okay, before, sorry. So you would get e to the x over 5. So e to the kx again, always get that back, and then 1/5 on the bottom. And this is between 0 and 2. Okay, so now we have to do a lot of evaluation. Actually, this won't be as bad as the last one, as you'll see in a moment. So we get 3. 2 cubed is 8, so you get 8 over 3. Subtract 0 when you put in 0. If you put in 0 to x cubed, you get 0. Plus 4 times 4 over 2 minus 0 plus 5. And now here we have to be a bit careful. Okay, so if you have 1/5 in the denominator, that becomes a 5 in the numerator. So it's actually 5 e to the x over 5. You put in 2, so you get e to the 2/5. Now when you put in 0, you don't get 0. E to the 0 is 1. So it's actually 5 e to the 0, but I'll leave it that. For now, just remember, you do not get 0 here. So this is, okay, we can do some more algebra. So this is the 3's here. the 3's here will cancel. And the 4 here will cancel to give you a 2. And so you're going to get something quite nice. You're going to get 8 plus 4 times 2 is 8 plus 25 e to the 2/5. And you get minus 25. Like I said, e to the 0 is 1. So just minus 25. So we get 16 minus 25 plus 25 e to the 2/5. So 16 minus 25 is minus 9. And so plus 25 e to the 2/5. And that is the exact answer. Okay, we won't put that in the calculator. If the homework asks for an exact answer, that is your guy. So just to summarize, the integral from 0 to 2, 3x squared plus 4x plus 5 e to the x over 5 dx was equal to 25, I'll write this way, e to the 2/5 minus 9. So that's the exact answer. Okay, so basically you see that this is just computing definite integrals for a different purpose than what we were doing before. That's all it is. You can take this a step further, so we can also use definite integrals to compute the area between two curves rather than just the area underneath a curve. Okay, so suppose we have this following kind of situation. I'll draw the picture first. I think the picture speaks 1,000 words. You have x equals a. Here, x equals b. Okay, and then you have, say, curve f lies on top and a curve g that lies on the bottom. So we have f and a g. And the curves meet at A and B. Okay, so that's the picture we have. I'll shade the little thing between the curves. Not a great picture, I admit. Let me fix this so you have like this. Okay, so that's the situation, and we want to find this area in purple. So the shaded area in purple is the definite integral a b f at x minus g at x. So the integral from a to b of f minus g at x dx. Now, this is basically very, very easy because why is this the area between the curves? So how do you get the area between f and g? Right, well, one way to do this is to take the area. So f is above g, right? In this picture. So you can take the area, so under f, say that's in red here, and then you can subtract the area under g, right? And that will give you the area between f and g. And that's exactly what we're doing here. That's exactly what this difference is. So take area under f and subtract area under g. If you do that, what is that? Well, that's integral from a to b fx dx minus the integral from a to b gx dx. And that's exactly, by our proper difference rule for definite integrals, that's exactly the integral from a to b f at x minus g at x dx. Okay, so unfortunately, in some of these examples, they don't give you the picture. So they're not going to give you this, well, picture's been totally shaded now, but to give you this little blurb between f and g. In other words, you won't know which function is f, which function is g, which function's on top, which function's on the bottom. And so it really, really helps if you can draw sketches, like very rough sketches in this situation. So we'll do an example, and then I'll be happy to do more in the live session. So let's see here. Example. Find the area enclosed by the curves y equals x cubed and y equals 2x squared, and the points where they intersect. Okay, so this is how the question, the book phrases the questions. It's a little bit not the right order. I mean, to find this area be closed by the curves, you need to figure out, if you go back to the picture, you need to figure out the points where the curves actually meet. So the first thing you're going to have to do in some sense is figure out the intersection points. But really, even better than that, to figure out which curve goes on top, you should draw a sketch. So first, we draw a rough sketch. Sketch of the situation. So the parabola, right, 2x squared is a stretched parabola. And again, the sketch doesn't have to be perfect. It just needs to be like roughly correct. The parabola just has to be going to the origin and kind of facing up the right way. If you don't need to draw the stretch perfectly. And then the cubic curve, you should kind of know how to draw that. We talked about it many times. It looks something like this. I'll clean it up. And then it kind of goes down like this. So we want the region enclosed by the two curves. That's this region that I'm going to shade in blue here, right? So clearly one of the intersection points is 0. The other point I'll call B, right? And the area we're after is, we can also see from this picture that the curve that's on top, the F here, use purple, the F at X, the one on top is the parabola, and the curve that's on the bottom, the G at X, is the cubic curve here. So then G at X is X cubed, is the curve that's on the bottom. Okay, so the area we're after is given by the definite integral from 0 to b of the top curve 2x squared minus the bottom curve. Okay, but to do this integral, to evaluate this integral, we got to find this unknown point b. We got to find the second intersection point b. Okay, but to evaluate the integral, we clearly need to find the second intersection point of the two curves. Okay, so i.e. the value of b. Now, to find where the curves intersect, hopefully you've done this in like a pre-calculus class, but what you do is you set the two curves equal and you solve for x. So to find where the curves intersect,
we set the two curves equal. And solve for x. So you would get 2x squared equals x cubed. Right, so that's exactly where the two curves meet is where you have an x value that gives you 2x squared is the same as x cubed, and then that'll be these points, right, where the curves meet. So we just need to solve for x, so we can kind of just do this. So we can bring over the 2x squared to one side, to the right side, factor an x squared with x minus 2. You have two solutions. One solution is x equals 0, and the other is x equals 2. We already knew about 0 because we'd drawn the graph, but if you hadn't been able to draw the graph, you'd have to do this. And so the missing point, the point we're missing, right, the second intersection point is 2. So this point is 2. So the second point, where the curves intersect, is b equals 2. And so the integral we need to compute is the integral from 0 to 2 of 2x squared minus x cubed dx. And now we can just do this thingamajiggy where we split it up as normal. We're kind of home free now. This is not a hard integral. And so you get 2, 0 to 2 x squared dx minus 0 to 2 x cubed dx. And so you get 2, the antiderivative of x squared is x cubed over 3 between 0 and 2 minus antiderivative of x cubed. Actually, this was one of the first ones we computed. It's x fourth over 4 between 0 and 2. And now we got to do some algebra. So you get 2, 8 over 3 minus 0, minus, and watch the minus here, 16 over 4 minus 0. So this is 16 over 3 minus 4, right? And so you got to add these fractions. You could do this on a calculator, but I'll just do it by hand. So it's 16 over 3 minus 12 over 3. And so that's 4 over 3. So as we draw I can just bring the picture back here, drive the point home. Okay, so this point, this value of b, the second intersection point we found, this had value 2. The cubic curve was on the bottom, the parabola was on top, and the area of the shaded region in blue here blue was 4/3, or is 4/3. It still is 4/3. Okay, so let me just make a point. I mean, you should always try to draw a rough sketch. And in my opinion, the questions on the homework are easy enough to be able to do that. They're nothing like too crazy where you can't just draw a rough picture. It doesn't have to be perfect. You just have to draw the picture to figure out like which points are on top,
sorry, which curve is on top, which is the F and which is the G. And then you'll have to find the intersection points if they're not given to you. With that, but you do that the same way that we did here. So let me just say a remark, but if you can't do that or if you screw up, then you'll get a negative number. So if you have the wrong curve on top, i.e. made the wrong choice for F, then the integral you get, the integral you compute, AB f at x minus gx dx will be negative. So if you have f and g reversed, basically you have the negative of what you want inside here. And the integral you get will have a negative value. And area should never be negative. So what you do if instead is you just, rather than go back and do everything all over again, if maybe you won't have time, you just make the answer positive. Assuming you've done the integral correctly. If you've messed up the algebra of the integral, you have the wrong number. But if you did the integral correctly and you just messed up which curve was on top of the other, then all you have to do in the end is you'll get a negative number and you just make a number positive. And then to get the right answer, just drop the negative sign. Okay, so it's not that bad, but try not to get into that situation because you might panic, you might freak out if you get a negative number. Just draw the sketch. It's not that bad. There might be one problem on the homework. If you have problems with it, I can help you through it. And we should be okay from there. All right. Thanks for tuning in.